Okay, so sequence, remember? Okay, noise. Sequence is a set of quantities arranged in a definite order, often referred to as a succession of terms. In previous courses, we have studied arithmetic sequences and geometric sequences, and some other miscellaneous ones, but really, that's what we focused on last year. Okay? So we're really going to look at geometric just because of the fact that it relates to exponential functions. So a series is the indicated sum of the terms of a sequence. We've studied both arithmetic and geometric series in previous courses as well. So, arithmetic sequence, what do we call, what's the pattern in an arithmetic sequence? What are we looking for to determine if it's arithmetic? Common difference. Keep adding the same number, whether it's positive or negative. Okay, so there is a common difference between consecutive terms. There might be adding a positive or adding a negative. Geometric sequence, what do we call that? You can tell me what happens in a geometric. What else? Common, not a factor, but you're on the right track. Yeah, in a way, except in these we call it the common ratio. So you use the letter R to represent it. Here we use D, lowercase. Here we use common ratio. Because basically the ratio between consecutive terms is common. It's the same. Ratio is like a division, right? Okay, so take a look at those terms there. Don't be tricked. You just learned about logs. Okay, and exponents. So figure out and just label arithmetic, geometric, or numeric. Once you've done that, see if you can remember all the formulas you learned last year.
Don't remember? No, you can write it. No, seriously. That's what I do. If I forget a formula, I'm rewrite it.
Okay, you don't need to talk. You just silently evaluate the terms in those series, because they're added together, and see if there's a common ratio or a common difference. So don't be fooled. Just because the arguments keep getting multiplied by 2, remember, when you do that, you can use the product law and separate the logs, right? So the product of 8, for example, can be shown, the log of 8 can be shown as the log of 4 plus the log of 2. Okay, this 16, log of 16 can be shown as the log of 8 plus the log of 2. You keep adding log of 2, which is 1. So evaluating, you see here, it's arithmetic with a common difference of 1. This you can't tell, right, because it's not, the exponents are all the same, but you can't just divide or multiply each consecutive base of that. So, and it wouldn't be consistent anyway. So evaluate. That means square root. So that's 8, 7, 6. So that as well is arithmetic. But now your common difference is negative 1. Okay, C is neither. No kind of sequence not T-sequence yet. So start with, it's a recursive definition, so you need to be told that T1 is 2, T2 is 3, then T3 is the sum of the previous two terms. T4, oh, no, just joking. I thought it was, so this is, but when I look here, 7 is not 3 plus 5. 11 is not 5 plus 7, so this is neither. And it's neither no matter what, but I thought we could actually be specific and label it in there too. Oh, that's forgot to look closely. Okay, so you're remembering your sequences and series. Arithmetic and geometry. So, arithmetic. So for sequences, we're just finding a general term. Okay? So we're going to use T's. Sometimes we'll get into the IB, might use U's. Okay? So, but in Alberta, certainly we use T's, and that they'll still accept that if you use it on an IB exam. Okay, so how do you get the general term, Tn? What do you do? What's the formula?
Well, I just use A.
Yeah, T1, the first term. You can use A if you want. And then you keep adding D, but to get the general term, it's got to be n minus 1 times D.
It's basically just the same thing for the geometric, but always an operation.
It's a multiplication, right?
Yeah.
So this is Tn equals the first term times the common ratio to the n minus 1.
Oh, I also derived the formula for geometric product, like product of geometric sequence. Basically the same way you derive for an arithmetic series, but all everything up instead of adding and multiplying. I'll show you later.
Okay, so arithmetic series, you're adding all of the terms in the corresponding sequence together. Okay, so this is, you may have seen when you learned about this, I show my class way back when young Gauss wanted to find a fast way of adding the numbers 1 to 100. He was in grade 2, I think.
Yeah, Gauss is kind of a genius.
Okay, so we realized that if you take 1 to 100, flip it around, right? We're trying to find the sum of all of those. If we have this, that means whatever these add together to, we get twice as much as what we want. So we would divide by 2 in the end. What you notice is each column there is 101. Okay, so how many 101s does he have? 100 of them.
Hey, Eric, how are you doing?
But I think I know where you're getting to, Eric, is that that's the total of this, which is 2 series. Now, if you divide that by 2, you get 50. That's probably what you're getting at, right?
Yes.
Yes.
Say yes.
Okay, so in terms of a general case, so what do we have here? 100 is how many terms? Over 2. Sometimes we show it up front, not as a whole thing. Bracket. What do we get for 101? Well, it's the first term plus the last term. Or the last term plus first, right? Or any in between, but it's the first term plus the last term. So that's one version of our sum of an arithmetic series. Okay. Yep. because we have two of these. Okay, now the other version is where, because sometimes you don't know the nth term, right? Whatever information I give you, you don't know what it is. So the other version is to substitute the expression for T1 in here and collect like terms. So that would be 2T1 plus n minus 1D. So these, you don't have to show all that work that I just did, but these are into some formulas for arithmetic. Okay, we will give these to you. You don't have to memorize them. We gave them to you last year too. Nope, you did not have to memorize them last year. It's not a bad idea to memorize them. It's never going to hurt you to memorize something. Believe me, when you get to my age, it helps. Okay? You've got to keep your brain going. You guys don't have to memorize as much stuff because you use technology a lot more, right? You have a lot of things in your phone. You don't even have to remember your own phone number, right?
You should remember.
Okay? So, it's not a bad thing to memorize. I've never been a great memorizer. That's why sometimes I find, like, I found, have you guys done any organic chemistry? Not yet? Yeah, I took that in university, and that was hard. Yeah, it was hard. Well, you have to memorize it.
Yeah, almost the entirety of things.
Okay, anyone remember that the infinite series sum is pretty easy?
Yeah, it's just a over 1 minus r.
Yeah. Or if I'm using t's, it's t1 over 1 minus r. So it's just flipped around, right? For these have r minus 1.
Well, actually, you can show that as also 1 minus.
Absolutely you can. But this is how we normally show it on the formula sheet.
And then just because I love the derivation of this, when you derive that infinite, is that you have an infinite sum. If you multiply every term by r, you still have an infinite sum.
Yeah.
But just starting with the second term, so you just subtract the factor of 1 minus r, divide, you have this. As long as r is not 1. And yeah, then it's just, oh, yeah, then it's just,
okay. Focus, please. Okay, so have those down to refer to when you're doing these questions, and we'll give them to you on the test. Okay, so review of sigma notation, sometimes called summation notation. Sigma is that symbol, the Greek symbol, sigma, okay, for S. So here, this is the index, K. So our first term is when K equals C, whatever this lower index is. So we would just show this as T subscript C, then T C plus 1. This is always natural numbers, right? Sometimes it actually might be whole numbers starting at 0 when you go on in math and do a little bit more. But for our case, we start at, we use natural numbers. So here, and then you keep on going. We don't know how many terms there are, but it's going to end at Tn. Okay, so the previous term to this, you can actually put it in there, T subscript n minus 1 plus Tn. Okay, if you had to show a series full length. As I said, sometimes IE uses use, so it doesn't change anything. Now it's using an index I. So this is going to be UC, not UC, but UC. UC plus 1. And same thing. This is going to be UC, N minus 1. Always look at what is up top there. Sometimes it's going to be a number. Sometimes it might be another parameter like this. Biggest thing to remember is that that number there doesn't necessarily tell you how many terms there are. It does if you start at 1. But we might start at a different number, so you have to have good attention to detail. Allie?
So what does, for example, K, what does the K stand for then?
K is the index, so it tells you which term. So the first term is when K is C. Okay? So this is what's called the index of summation. So you have to follow this through. So when K equals whatever this number is, that gives you the first term. You add 1 to that to get to the next term. And then you'll substitute in to the formula, whatever it is. Okay, so here's an example. As I mentioned, there are not 17 terms. So please, read in the math class that you don't tell me there's 17 terms. Just think a little bit more. Okay, so how many are there? You can tell me. Do you think there's 14? Hands up. Think again. 15. You need to include the 3. N equals 3. So use your fingers if you need to. N equals 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 15. I did that 5 times. So it's going to be 17 minus 3 plus 1. Right? To include that first value. Okay? If you subtract 3, you subtract it, if you think about it, the first term, second term, and third term if you were to start at 1. So there are 15 terms. What kind, just looking at it, what kind of series do you think it is? Arithmetic or geometric? Arithmetic. The variable is not an exponent. So you can always test it, but looking at this, arithmetic. Remember back to all the work you did with sequences and series last year with arithmetic. Yeah, well, you're going to have to. Then when you use that TN formula, we always simplify it, right? To get it in an expression. So linear expression. Okay, so to evaluate this, again, you can maybe figure out without doing much work, but I always write out the first few terms just to make sure I get that common difference correct and my first term correct. Because my first term isn't necessarily that constant term. For sure it isn't in this one. So this is equal to, when n equals 3, that's 15 minus 3 is 12. When n equals 4, 20 minus 3 is 17. Okay, so yeah, the common difference is 5, but the first term is not negative 3. Then if we want to do the last term, because we know it, then what's 5 times 17? 50, 85 minus 3 is 82. Now this is not terrible, 15 terms, but as I told my class last year, if you're in a test, and you can check, but this is really annoying. And then usually you miss one when you've done one too many. Okay? Because once you get past about 15 or 20, it's hard to keep track of it. Okay? So, because I know the last term, I think I'm going to use actually I'll write the formula out first over here. I'm going to use the n over 2 times t1 plus tn formula. Just because I know that last term, I already did that work. So now this is S15 equals 15 over 2 times, in brackets, 12 plus 82. And you can just find the value. I don't really need to see the order of operations of that. Okay, so then this one, determine K if we're given the sum. Obviously, if it's in a numeric response or multiple choice, if it's multiple choice, you could just substitute that K value into your sum formula and find the one that works. In this case, let's do the algebraic full solution for this. So this is the same series as the previous one. We're just trying to find K. So here, 546. I'm not going to use this form here because I don't know what that Kth term is. Although you could, because you could substitute K into the general term. But I'm going to use, in this case, that's going to have to be, so here, and you got to figure it out. So remember, it's upper index minus the lower plus 1. So that's going to be K minus 2. So K minus 2 is your n over 2. 2 times the first term plus n minus 1. N is K minus 2. So K minus 2 minus 1 is K minus 3. There times our common difference, which is 5. So it's going to be a quadratic. So you got to expand that out. Get everything on one side and factor it. Quadratic formula. If this was a numeric response or multiple choice, then if you've already done part A, right there, our upper index was 17 and our sum was 705. Here our sum is 546. It's smaller. So you know your K value has to be smaller than 17. You could work backwards from it. But we're showing a proper algebraic solution, just in case you have to do that. No, 1,000. 100. Yeah. Okay. If you're you're not good at factoring that, what can you do? If you're trying to find k, it has to be factorable. K has to be a natural number. If those are too big numbers for you, you just hate it. Finding those two, what can you do? Other than the quadratic formula.
Graph.
Graph.
What's your calculus?
Well, then you can't. That's the whole polynomials unit that you did last year and this year. Better not forget about it. I don't know. We could go, it's quite a big number, so let's go negative 20 to positive 20. We don't care about the y's, really. So negative 10 to positive 10. Okay, so I see two x-intercepts. Actually, I'm going to graph y equals 0. That's a little easier. Second trace intercept. Okay, negative 14.8. If I want to see if the other one is okay, this is taking longer than doing that, right? It looks like it is 15. Okay, it is 15. So this is going to be k minus 15. And that was 14.8. So you don't even know how to convert that. Your calculator does it. 74 over 5. So that's going to be 5k is negative, so plus 74. Okay. Okay, k can't be a fraction or negative. So that means k is 15. Okay, so that one was arithmetic. Have a look at example 2. Notice how the k is in the exponent. So likely it's geometric. Just be a little bit careful on this one because it's 3 minus k. Not possible. Okay, so number of terms in this, if it starts at k equals 1, then it's just 12. 12 minus 1 plus 1 is 12. Okay. Every time you change k, it's changing the exponent on this 1/2. So it's going to be geometric. If you're not sure, throw a few terms. So I'm going to do that here anyway. When k equals 1, I get, you can write it out, 3 times 1/2 to squared. Then 3 times 1/2. When k equals 2, that would be 1. 3 times.
Right, wouldn't it be nicer if you could like switch around the k minus 3 and then 2 to 1/2 times 2?
Yeah, you can. Then here, this will be 1/2 to the 3 minus 12 is negative 9. Okay, so this is going to be 3/4 plus 3 over 2 plus 3 and whatever that's 2 to the 9. But 12 times 3 is, okay. So the common ratio is not 1/2. Common ratio is 2. That's because, as I mentioned, that's a negative k there, not a positive k. Your normal Tn for geometric is, so the term number is positive here in the exponent. This is negative. So it's flipping that base.
You can also think about it, divide the first term by the second term. Or sorry, the other way around, second term by the first term.
Yep.
Again.
Yep, to get the common ratio, 2 consecutive terms, the second one divided by the first, or the third one divided by the second. Okay, so the sum of the 12 terms, so you have a couple of choices. Okay, so these two, obviously it's not infinite, so we're choosing between these. We do, listening folks, because I calculated the last term, I can use this. But again, if you didn't calculate it, then use this one. So really it's up to you. So, common ratio. So I should put that over here actually. So here the common ratio is 2. I'm going to use Sn equals r times t n minus t1 over r minus 1. So 2 times the first term, the last term. Minus the first term, all over 2 minus 1. Okay, again, I don't need to see the work in between. You can, as long as I see the number substituted correctly. Obviously, 2 minus 1 is just 1, so you don't have to do that. So that as a decimal, but we'd like to show things, even though that's actually an exact value, often we'll say in fraction form. Let's take a look. When you do math graph, sometimes it won't convert it. Okay, so that, you actually have to know fractions. Heaven forbid. So, what is that? 3071 and 14. Okay, back to elementary school, junior high. So 3071 times 4 plus 1. You can always check that, put that in, and make sure you get the decimal form.
Oh, so far this is all just right?
Correct. Now, this is obviously bigger than this, so our B value is going to be bigger than 12, right? Again, use some common sense depending on how the questions are given to you. But again, algebraically, it does say determine, so we have to show work. So here, that's going to be our sum. Okay. We don't have the last term. So we can't use that same formula. So we have to use the other formula, which is T1 times r to the n minus 1 over r minus 1. This is not n minus 1 in the exponent. Sometimes students mix that up. Look at your formula sheet. Read it carefully. So this n would be b. Okay, 2 minus 1 is 1, right? There's 4's in the denominator, so I'm going to multiply both sides by 4. And then you actually multiply by 4, divide by 3, because it's really, you're dividing by 3/4, so you can do it all in one step, or 2 steps. And then 2 to the b, you're going to add 1, so that would be. So remember, b has to be a natural number, so we should be able to solve this without logs, right? Because we should be able to find a power of 2 that equals this. So guess it in your calculator. Yes, you can use logs. You can also go, okay, I'm going to test out. I know it should be, the last question was for, and was 12, so let's go 14. Ooh, not even close, right? So, let's do 2 to the 18. Nope. 2 to the 22. Nope. 2 to the 24.
Oh, you already went over.
Oh, did I go over? Oh, yeah, I did. So that's this divided by 4, right? So 2 to the 20. You can use logs, yeah. Okay, then example 3 is an infinite series. Infinite geometric series. For an infinite arithmetic, there's no sum formula because it does not converge to a number. Okay, so you can have infinite of any series, but you're only going to be finding the sum of infinite geometric. Okay, so remember what the R value has to be. Less than 1.
Okay, my analytic. I'm just going to stop talking.
Alright, so here, first term is going to be when I is 1, so that's 24 over 4 is 6. Second term will be 6 times 3 is 9 over 2. Okay. Pretty clear here that your common ratio is 3 over 4. No, not clear. So this divided by 6. Is 1,
Yeah.
3/4. Yeah, it is 3/4. What am I thinking? Yeah, it should be 3/4 because of the power here. This I is positive, so you keep multiplying by 3/4. I don't know, I had a brain freeze. We're going to set it back there. Everyone okay? we've done an arithmetic, a geometric, and infinite geometric. Example 4, example 5, we will need for you to do on your own. Okay? So you're going to do that one. Okay? So 4 and 5 you're going to do. Let's look at 6. Expressing a series in Sigma notation. It's not really a terribly challenging, but in terms of notation and having good attention to detail. Okay, so what you want to look at, first of all, is decide what kind of series it is. So here, the actual terms, notice that they're decreasing by 20. So this is an arithmetic, so it has common difference of negative 20. Okay, don't just check the first, because maybe then it's a geometric, but then check the next 2 consecutive, right, to make sure it's the same. So in our sigma notation, we can use whatever index. I often use k, and if I'm stating this, I always start at k equals 1. If you start at k equals 1, then you can just use the general term formula. Okay, so for arithmetic, remember the general term formula is that. So I want to do that for these terms here and simplify it. We always wanted to simplify. So in this case, Tn would be 100 plus n minus 1 times negative 20. When you substitute a negative value into d, please put brackets around it. If you don't, it looks like you're subtracting 20. Even if you don't subtract 20, that's what it looks like it should be, which is not what it is. Simplify in here, so you're going to get negative 20n plus 120. You can show it 120 minus 20n, even though that's not descending order of degree. It's actually fairly common to show it that way. Now, though, I'm not going to put n in here. I'm going to replace n with k, because that's my index. So I'm going to go negative 20k plus 120. And then, in this particular summation, I do have a last term, negative 200. So now I can solve for n here to know what my upper index has to be. So if I do that, that's negative 320 equals negative 20n. So n equals 60. So my upper index is 60. Okay, again, when you're looking here, don't look at just the first 2 terms. Anytime that it's alternating, well, you actually don't know, I guess, if it's, yeah, if you just look at that, then maybe you're adding a negative. But here it goes back to being positive. So that's a hint that likely is geometric. Just make sure it's a common ratio. If it's neither, then you can't use those formulas. Maybe you can find a formula for the general term. Doesn't mean you can, but it's not going to be arithmetic or geometric. So here, you can go negative 90 over 270 to get your R. That reduces to negative 1/3. So second term divided by first term. Then you can check it out. If I multiply negative 90 by negative 1/3, I get positive 30. Or 30 divided by negative 1/3. So it's geometric. So Tn would be T1 times R to the n minus 1. T1 is 270. Common ratio is negative 1/3 to the n minus 1. like that. You could actually do a little bit of simplifying. It's 27 times 10. 27 is 3 cubed. You could combine that here. But for today's purposes, we're not going to do that.
Actually, you can even make it even nicer, I guess. If you can say A is equal to 0 and then just keep okay. That works.
Yep. Okay, so if we do this, then K equals 1. I need to copy this out and put K in instead of N. Notice how there's no last term there. So I just put infinity in. Okay, so there's some notes there on calculator operations for sequences and series. I'm going to leave that for you to do on your own time. It's not going to be on the test. It's just kind of interesting for you to be able to generate the terms in a sequence, that kind of thing. So that calculator part is up to you. If you take HL, we'll kind of look at this again in terms of the calculator, but you're not going to be asked to use it specifically. Remember, we've kind of done a fair bit of testing on this. Well, you guys were doing COVID, I can't remember. Did we test while you were online last year? Yeah. So hopefully you remember it. Hopefully it was your own work. Okay, so then the last part here. So ID notation for sequences and series. So as I mentioned, sometimes ID uses U. In their data booklet, you might see UN equals 1 plus n minus 1. Okay. As well, you'll see this little bracket notation. I call those squiggly brackets. Okay, but they're squiggly, not round. Okay, so this will tell you the term. So that will be a general case in terms of K. So it's kind of like in summation notation where the index is at the bottom and the maximum value of that index, the upper limit, is at the top there. Okay, and so this will be your formula for any term. Okay, so it says express the following sequences in that form. So we've already practiced with series. Series, we find that general term, but we put it with the sigma because those terms are added together. These ones aren't because it's a sequence, but we're going to have that squiggly notation. K equals 1. We're going to have to figure out which term it goes to, and we have to figure out what the general term is. So take a look. If I'm adding 2, it doesn't work, right? So 4 divided by 2 is 2, 8 divided by 4 is 2. So this is geometric, where my first term is 2, my common ratio is 2. Okay, so you could really simplify that because your first term is 2 and common ratio is 2. I don't know, you're playing a game or... So this is 2 to the 1. Multiplying those together, you add the exponent, so that's going to be just 2 to the n. Okay, so you can simplify that one. So in here, I'm going to put 2 to the k. And then I need to solve. I need to know which term it is. Okay, so that's equal. So 256 is what? 2 to the 6, 7, 8. Yeah. Okay, so n equals 8, so this will go to 8.
No, definitely do not use square brackets or something else entirely.
Here, this is geometric as well, right? We keep multiplying by a half. So this is kind of the same. It's going to be a half to the n. Goes on forever. So when we do this, this will be 1/2 the k. K equals 1. But that's going to go to infinity. And I guess you could go 1/2 equals k. Yeah. Okay, so then we've got the next one, we've got an infinite geometric series. So our terms are u1, u2, u3, etc. Sn will denote the sum of the first n terms of the series. So remember when we talked about series last year, so S1 is going to be the same as the first term, right? Because there's only one term. So those are the same. S2 will be the sum of the first two terms. S3, sum of the first three terms, and so on. We call these partial sums. You're finding basically a part of all the sums of that infinite series. Okay. So Sn is called the nth partial sum of the series. And so we can also show that in bracket notation.
How do you tell the difference?
It'll be given to you like this equals. So you know it's sum. S's. Okay. So that's going to be the sequence of partial sums. So in this case, Sn represents the nth term of the series, right? The nth partial sum. So example 10 gives you, so it says we've got a sequence. So you know that is the notation for a sequence. So now find the first 5 terms of that sequence. Then find the first 5 sums. Just manually. Okay, so 1, 2, I don't know why we put positive infinity. It's understood to be positive without that.
Yeah, no, we're not doing negative terms. Negative and no.
Okay, so the first 5 partial sums. So remember, these are equal. S2 is going to be the sum of these two terms, so it's 24. And then the sum of the 3 terms, or you can go S2 plus U3. And then next one is S3 plus U4. And then 30 plus 1 is 31. reaching a little, another brain freeze here. Because that does not form, so a formula, we have to find a formula for 16 to 24, 2 of these is a sum. So remember for a geometric, so first term, so we're going T1 part to the n minus 1, part minus 1. So your finding the first term of the series is 16. Your common ratio of that corresponding sequence is a half to the n minus 1 over 1/2 minus 1. So if we simplify this, that's going to be what? 1/2 minus 1 is negative a half. So that's going to be negative 32 up front here. Okay, so that will give you each sum. So let's check it. If I put 2 in here for n, I get a 4. So I would get 2 would be 1/4 minus 1 times by negative 32. 1/4, yeah. I don't know where my brain is. In any case, so this is our sum n. So this is going to be negative 32 1/2. And actually, I'll use k. I like using k. Sorry about that. I'm not sure what happened in my head.
And you can also just expand that out.
Yeah, you could. This is 2 to the 5th, so you could expand. You still have to then add 32, but it would be the same. That's fine. Okay, and then do a quick graph. So sometimes we graph sequences in series. So n is always the horizontal. In this case, the term value is the vertical. In this case, the partial sums are the vertical. Don't connect them. They're discrete values. Discrete. Okay, so because the common ratio is 1/2, remember it's a decreasing exponential function. It's not continuous, but still follows that pattern. Okay, so that's what the graphs will look like. Let's think about this. If this goes to infinity, okay, you know our first term 16. So our infinite sum is It is convergent because the common ratio is a half. So our first term is 16 over 1 minus a half. No, a half. Yeah, 1 minus a half is positive. Okay, so that means here, you'll notice that at n equals 5, that's 31. So this, as n goes to infinity, over here is going to approach 32. All those values. So it levels off. That's an asymptote at 32. Okay, so there are some exercises there to work on. Then there's also geometric sequences and series questions. Good practice on those. I'll do a bit more graphing tomorrow.